The year of 1809 stands as a pivotal one in the annals of celestial mechanics, indelibly marked by the publication of Carl Friedrich Gauss' Theoria Motus Corporum Celestium in Sectionibus Conicis Solum Ambientium. This magnum opus, a culmination of Gauss' relentless intellectual pursuit, transcended the mere calculation of planetary orbits. It became a cornerstone of observational astronomy and a testament to the power of mathematical rigor in unraveling the mysteries of the cosmos. A consideration of this work necessitates a journey into its genesis, its profound contributions, and its enduring influence on subsequent generations of scientists. The intellectual climate that birthed the Theoria Motus was one of intense scientific ferment. The late 18th and early 19th centuries witness to burgeoning interest in astronomy fueled by the invention of the telescope and the burgeoning understanding of Newtonian physics. However, certain observational challenges persisted. The recovery of lost celestial bodies, particularly comets and newly discovered minor planets, presented a formidable challenge. Existing methods for orbit determination, largely iterative and cumbersome, often proved inadequate when faced with limited observational data. These methods frequently required long observation arcs, spanning weeks or even months, to yield reasonably accurate orbital parameters. The discovery of the asteroid Ceres in 1809 provided a dramatic illustration of these difficulties. Within weeks of its discovery, Ceres was lost behind the glare of the Sun. The only available record of its orbit consisted of a handful of observations taken over a limited period. The problem of predicting its reappearance, therefore, posed a crucial test of the state of celestial mechanics. Gauss, a prodigious mathematician since childhood, possessed an inherent aptitude for problem-solving, with a particular penchant for numbers. While still in his early 20s, he tackled this challenge, not simply by refining existing techniques, but by developing a novel methodology. This brilliance was already evidenced by the publication of his Disquisitiones Arithmeticae in 1801, a work that revolutionized number theory and provided him with the mathematical foundations necessary for his astronomical endeavors. Gauss' genius truly lay in his ability to connect disparate mathematical ideas, crafting tools, that went far beyond the immediate needs of observational astronomy. The Theoria Motus presented a complete, self-contained treatment of the problem of orbit determination. The cornerstone of his method was the least squares method, though the term was first used by Legendre. However, it was Gauss who provided the theoretical justification and the systematic application of the procedure. The foundation rested on the principle that the best estimate of a quantity is the one that minimizes the sum of the squared errors. Imagine multiple observations of a celestial object, each with some degree of observational uncertainty. Gauss' method allowed astronomers to fit an orbit to these observations in a manner that minimizes deviations of the estimated positions from the observed positions. This approach offered a unique advantage over earlier techniques through its ability to incorporate data from multiple points. It allowed the derivation of the most probable orbit from only a few observations, even those separated by small time intervals. The resulting orbit was the one that best harmonized with the existing data, thus providing a more robust and accurate estimate of the orbital parameter. The mathematical apparatus Gauss developed was both innovative and elegant. He introduced a rigorous framework for understanding the propagation of errors, enabling astronomers to quantify the uncertainties associated with their orbital predictions. Gauss' approach made explicit the interrelation of the data points. He included considerations of the effects of observational errors in different directions and the associated uncertainties in the orbital elements themselves. The method provided specific procedures to compute the orbit from the data of the observations. His derivation of the equations for orbit determination was nothing less than a feat of mathematical creativity. The equations could be solved irrespective of the number of observations. It facilitated the derivation of a closed-form solution. The computational burden was shifted from that of repetitive trial and error to systematic arithmetic. The immediate impact of Gauss' work was nothing short of transformative. The recovery of Ceres, a feat accomplished in December 1801, a year after its discovery, was a pivotal success. By using his method, Gauss was able to predict the asteroid's position with remarkable precision, allowing astronomers to find it again. This triumph not only validated his mathematical approach, but also established his reputation as a leading mathematical figure and a champion of observational astronomy. The recovery of Ceres stood as a testament to the power of his mathematical methods. The methodology provided astronomers with a robust tool for orbit determination, enabling more accurate predictions of celestial body motion, thereby facilitating further discoveries and furthering the understanding of our solar system. The Theoria Motus went far beyond orbit determination. It contained a comprehensive discussion of the theory of conic sections, spherical trigonometry, and the effects of perturbations on planetary orbits. The book served as a comprehensive textbook, guiding astronomers through every step of the computational process, from data acquisition to the refinement of orbital parameters. It provided detailed computational processes and procedures, eliminating the need for arduous and intricate methods. The book demonstrated the power of systematic and rigorous mathematical approaches in astronomy. It provided a template for solving a range of problems that confronted observational astronomers during this era. The meticulous detail, the elegance of the mathematical derivations, the thoroughness of the examples made the Theoria Motus an instant classic. The influence of Theoria Motus reverberated throughout the scientific community. It influenced astronomers like Olbers and Piazzi. Their observational precision was further refined, improving the accuracy of their calculations. The methodology became the standard for orbit determination in the 19th century, with its application extending to comets, planets, and even binary stars. As observational techniques and instruments improved, the mathematical rigor of his approach influenced mathematicians like Poisson and Cauchy, spurring further developments in probability and statistics. His least squares method became a fundamental tool across many scientific fields. From geodesy to economics is still used. The reception of the work, although largely positive, was not without its complexities. Some contemporaries, accustomed to more empirical approaches, may have found the mathematical sophistication of Gauss' work daunting. The techniques he introduced were initially difficult for some astronomers to follow. The publication of French translations and later editions over time helped to further expand its accessibility. Furthermore, as new discoveries such as Uranus were made, the methods had to keep pace. As the more eccentric orbits of newly discovered celestial bodies demanded continuous improvement to the computational techniques, Gauss' approach was subsequently adapted and refined by many astronomers. His work had a profound impact on the development of error analysis and statistical inference. The mathematical tools, such as the method of least squares, gained widespread adoption across scientific disciplines. The impact of Theoria Motus extended beyond the immediate sphere of observational astronomy. The work's introduction to the field of probability provided a theoretical basis for assessing the reliability of experimental measurements. His emphasis on error minimization had a profound impact in the field of precision measurement. It enabled the development of more reliable scientific instruments and experimentation setups. The enduring legacy of Theoria Motus can be seen in the modern practice of astronomy. The method of least squares remains a foundational tool in data analysis. Observational astronomers continue to apply the principles of error analysis and statistical inference in their work, tracing their origins back to Gauss' pioneering efforts. Modern computer algorithms for orbit determination, while employing sophisticated computational techniques, are still rooted in the principles and methodologies that Gauss established. The Theoria Motus remains a landmark achievement, a demonstration of the power of mathematics to explain the cosmos and the legacy of Gauss. His influence extends beyond the technical details of his work. It reflects a dedication to mathematical rigor and a commitment to understanding the natural world. His methodical approach, his insights into the structure of data, and his unwavering commitment to accuracy have played a crucial role in shaping the development of astronomy and science in general.